So going over page 9 here, let's take a quick look. Number 1, Nellie Newton holds an apple weighing 1 Newton at rest in the palm of her hand. The force vectors shown are the forces that act on the apple. So there's a normal force up and there's a weight acting down. So A, to say the weight of the apple is 1 Newton is to say that a downward gravitational force of 1 Newton is exerted on the apple by, hopefully you said, the earth. B, Nellie's hand supports the apple with a normal force N, which acts in a direction opposite to W. We can say that they're equal in magnitude because the apple is just sitting there. It's at rest. So since the apple's at rest, the net force on the apple is 0. D, since N is equal and opposite to W, we either can or cannot say that they are comprised an action-reaction pair. Well, they are not, and that's because they act on different objects. Here we see N and W both acting on the apple. So action-reaction pairs have to act on different objects. E, in accord with the rule, if action is A acting on B, then reaction is B acting on A. So if we say action is Earth pulling down on the apple, the reaction is the apple pulling up on Earth. So to repeat for emphasis, we see that N and W are equal and opposite to each other, but they do not comprise an action-reaction pair. So if you read the little blurb in there, that tries to reiterate this point. G, another pair of forces is N, and the downward force of the apple against Nellie's hand. The force pair isn't an action-reaction pair. Suppose Nellie now pushes upward on the apple with a force of 2 newtons. The apple, will it still be in equilibrium? No, it's going to accelerate upwards. And compared to W, the magnitude of N is going to be twice that because it was 1 Newton. So it was 1 Newton down and it would be 2 Newtons up and they would no longer be balanced. And so therefore it would start accelerating upwards. And then I, once the apple leaves Nellie's hand, N is 0. And the net force on the apple is only going to be W. So once it leaves the hand, it's not touching. There is no force there of N. And so the only force acting on it is going to be gravity. So how did this go? If it didn't go well, you might want to take a look at the Physics Classroom website, which is where this link is. They talk a little bit more about action-reaction pairs. There's a few other examples there. If you're confused, you might find that useful. But if not, you don't need to look at it. So I'm going to move on to the next topic and consider Newton's third law of motion. And instead of spending a ton of time kind of going over this, I am going to primarily focus on filling out your doodle note sheet. But first, I want to watch a really short video, and we're going to take a look at this.
So rockets, we've all seen rockets with the space shuttle takeoff, but how exactly does that work? Well, we're going to explain how it works very quickly by introducing a guy named Sir Isaac Newton. He lived about 300 years ago, British physicist, great haircut, and he came up with 3 laws of motion. Now, we're going to talk about his third law of motion, and to show you how this is going to work, we're going to be launching a Shaw rocket, which is kind of handy. This is our special limited edition Express Shaw rocket, and what we're going to do is we're going to launch it using a special rocket fuel that I've mixed here at the H.R. McMillan Space Center. Not something we recommend you folks try yourselves at home or the office. We're going to mix this together and try and explain what Newton was talking about. His third law of motion talks that for every action, there's an equal and opposite reaction. So what we're trying to do is to create an action inside our rocket. Our equal and opposite reaction is hopefully our rocket taking off across the stage with a very large explosion, which is what we want. So what I've done is I filled this rocket full of some fuel. I've poured most of it out, and what I've left inside are just some vapors. We're going to attach this to a specially designed safety cord, and we're going to ignite our rocket much in the same way that they ignite a real rocket. And we're hoping that we're going to get an action. In this case, the action is going to go this way. Our equal and opposite reaction is going to go in the opposite direction. So we're going to get this nice and tight, get this all ready to go. I'm going to put my safety goggles on, get ready, and we might as well do this. We might as well dim the lights. So we'll dim the lights, and in the darkness here, we'll see if we can get this rocket ready to go. Light our barbecue lighter. We're going to go from 5, 4, 3, 2, and 1. Well, a fairly successful rocket launch. It's going to blow some smoke rings for a little while, but you would too if that just happened to you. To learn more about rockets and Newton's other 2 laws of motion, come down and visit us at the H.R. MacMillan Space Center. For The Express, I'm Cam Cronin.
Right. So one of the most commonly used examples for Newton's third law of motion is that one, using that kind of an explosion and it moving forward. So hopefully you found that video entertaining. Everybody seems to like the explosion. So I want to go back and I want to fill in the doodle note sheet, which is the last one in that packet about Newton's third law. So this is back in that packet that was handed out back in chapter 2, but you also used it in chapter 4 to do Newton's second law. So we're going to finish this packet up today. So we've got here a number of things filled in. You may want to pause it and write some stuff down. So the most important concept here is that the action force acts on object 1 and the reaction force acts on object 2, whereas balanced forces act on the same object. So here we've got the action being Earth pulls on the satellite, and the reaction is the satellite pulls on Earth. However, we also know that Earth does not accelerate as much due to its large mass, and we're going to cover that in just a little bit. We are always going to have force pairs acting, even if they're at a distance forces like gravity, which is why you have this with a satellite. Using the law of force pairs, explain how a car accelerates. So the car tires grip the road and push the road backwards, and the reaction force moves the car forward because the road pushes on the car. So we've got here, and you do not have to draw this hockey player like to this level of detail. You can actually just draw it as a box. So we have an 80-kilogram hockey player, and he is going to have a force of gravity down, a normal force upwards, and you can use our abbreviations that we're using in class. And you're going to have a 65-kilogram hockey player with also a force of gravity and a normal force up. And those have to be balanced, otherwise the hockey players will either be levitating off the ground or they will be sinking into the earth. And you have a 1 force on going from the 65-kilogram player to the 80, and you have one going the other way. So if we have this one being the reaction, the other one's going to be the action force. I think it would be easier if you kind of drew these next to each other, but the person who did this didn't have room to do that. So then, true or false? When a bug hits a car's windshield, it splats because the force of the car on the bug is greater than the force of the bug hitting the car. And that's false. The forces are equal. Remember, it says they're equal. But the bug has such a tiny, tiny mass. It ends up having a larger effect on him because of his acceleration. And we were going to talk about that in the next video. So if you did not get all this copied down, pause the video before moving on, because I'm going to go on to the other sheet in this packet. So the very cover page, we have not done the third law of motion. So there are the 2 things here. So when one body exerts a force on a second body, this second exerts a force on the first that is equal in magnitude but opposite in direction. In other words, for every action force, there is an equal and opposite reaction force. This is how I'd like you to have it memorized. Okay, so for every action force, there is an equal and opposite reaction force, and you must use the word force, even though you are going to see it on the internet, in textbooks, and in videos without the word force. The reason I insist that you use the word force is because it is so commonly left out, and people think that it's this action and reaction are something different, but they are forces. So I think it's important to use the word force. So I am on page 5 in your purple packet. Some notes. So all of this means that the force that you push on the wall is equal to the force that the wall pushes on you. And the force that you kick a ball with is equal to the force that the ball pushes back on you. The force that the car's tires push on the road is equal to the force that the road pushes back on the car tires. And what happens as a result, the car moves forward. And while swimming, the force that your arms push the water back is equal to the force that the water pushes back on you. And then what happens is you move forward in the water. And is this really important? Yes, it is. This video is quite entertaining. I'm going to provide the link for you. It is a jetpack, and it is the guy from Veritasium who, it's kind of an entertaining video watching him maneuver a jetpack and what happens if Newton's third law of motion doesn't take effect. So with that, I'm going to close this one down and we'll move on.